Hi, good morning. I hope you are doing good. In today's video, I'll be talking about Autodock4 zinc force field. How to predict the binding affinities of small molecules on zinc-bound proteins. Zinc is considered one of the key elements or metal ions in almost 30% of the protein databases that we have, or the protein structures that we have. So it's really important to utilize the structures to predict the binding affinities that small molecules can bind to zinc bound proteins. You can apply the same for the Fe bound proteins or Cu bound, Mg bound, or any other metal ions. But this video will be particularly focused on zinc bound proteins. Let's begin. Thank you very much. So if you go to this particular paper called AutoDock4Zn, an improved Autodock force field for small molecule docking to zinc metalloproteins, I think this is the paper where they described how they have defined the force field for the zinc atom. They have placed a pseudo atom, and we'll be doing the same tutorial, and we can see that how we can perform the zinc bound metalloproteins docking with the small molecules, and this is the structure that we'll be focusing on today, which is 1R1Z. And this is the structure where I think you have the zinc bound to the protein. It's a metalloprotein, by the way. Yeah, you can see the zinc is bound here. So we'll be performing the calculation on this particular protein. I have opened these three tabs, as you can see, my terminal, the folder, and the tutorial itself. So we have taken this protein called 1R1Z, and this is the structure you can visualize using Chimera, and you can see that zinc is bound over here. And let me zoom in first, and you can see that you have the zinc bound to the protein itself. And then you have this small molecule, which we are going to dock today by using the Autodock4 zinc force field. And one more thing, these are the two files provided by the Autodock4 community, actually three files. And this is the DAT file or the parameter file where the pseudoatom, the zinc pseudoatom has been placed, and also the parameters for the zinc ion as well. So this is available in the default DAT file, the parameter.dat file. It's called AD4 parameters.dat or AD4 bound.dat. Okay, so this is the file that is provided by them. So I can upload it to my GitHub channel as well. Okay, so first we have to check the Python 27. I think the Python 2.7 environment, because MGL tools can only be installed via Python 2.7, not Python 3. Okay, so for that you need to create an environment, and you can create the environment by using conda create -n. You name it Python 27, and then Python is equal to 2.7, which will create the environment for Python 2 or Python 2.7 to be precise. Then you press Y, which is yes, and then it will create the environment for you. Now you have to activate by using conda activate your environment name, which is conda activate Python 27, and your Python 27 environment has been activated. So the next thing that you are going to do is you have to install the MGL tools package, which you can install it via conda install -c. -c is the channel name, which is bioconda, and then MGL tools. It will install the MGL tools for you, and you get all the required files for your analysis as well. Okay. So if you type in ADT command, it will show up the MGL tools window. That means your MGL tools has been installed properly, and all your scripts has already been installed. I will show you where it is located. So if you type in which ADT, it will tell you the path where the MGL tools has been installed. So this is the directory where my MGL tools has been installed. If you have installed it via Conda, then it will definitely be in the Conda environment MGL tools. I have installed it separately, so my directory is different. But you see this MGL tools package, and then you go to the Autodock4, and then where you have all the scripts over here. Okay, and there is a folder called utilities 24 that you can see over here, and there you have all the scripts required to perform the Autodock4 conversion of the files like protein GPF, and you can also prepare the PDBQT file, the ligand PDBQT file, etc. All the scripts are here in this utilities 24 directory. I think I have mentioned this in my previous tutorials also, where this is exactly, and you can find all of them in this particular directory. You can set up an alias for all these scripts in your bash RC, and then you can directly run those scripts on your terminal. Okay, so now we have these files. Okay, the first thing that we are going to do is we have to prepare the receptors. I mean, we have to convert the protein.pdb into protein.pdbqt. And this is the command, prepare receptor 4.py. It will create the protein.pdbqt file. Remember, the protein.pdbqt file that you have, it doesn't have the pseudo atom yet. This is only the pure amino acids. Okay. So the next command that we are going to do is we have to prepare the ligand PDBQT. And for that, we are using this particular script called prepare ligand 4.py. You provide the mol2 or STF or whatever you have, and then you create the PDBQT and add hydrogens, because hydrogen addition is really important for the ligand structure, even for the protein as bad, but we do have hydrogens in our protein as well. Okay, so now the ligand and the protein has been prepared, the PDBQT has been prepared. Now we are going to add the tetrahedral zinc pseudoatoms, which is the TZ. Okay, so the script that is provided by them is called zinc pseudo.py. So what we are going to do is we are going to utilize the Python 27 environment, Python 2.7 environment. So you have to type in Python zinc pseudo.py -r. You have to give your protein.pdbqt file, and then it will give you a protein tz.pdbqt. That means your pseudoatom has been added to your PDBQT file. Okay. Previously, when you have prepared the protein, it was only with the amino acids, 20 amino acids, but now it contains this pseudo zinc atom. Okay. Next, we are going to prepare the Greek parameter file, and this is the parameter file that has been provided by the Autodock4 community, where you have the TZ, which is your pseudoatom, and your zinc force field parameters. Okay, so this file I'm going to upload on my GitHub channel, so don't worry about that. You will get that. So you have to place it in this particular directory, and they also have provided a file called prepare gpf4 zinc.py, which is particularly meant only for the zinc metal ion. Okay, so that you can place your pseudoatom while preparing the gpf4. Okay, so the command is python prepare gpf4 zinc.py. You provide the ligand, which is -l ligand.pdbqt, and r with the pseudoatom.pdbqt, which is protein underscore tz.pdbqt, and then you output a file called protein tz.gpf with points 40, and then your grid centers, and then your parameter file, which is defined by -p, which is your 84 zinc.dat. And you open this, you have the gpf4 the GPF file has been prepared with the pseudo atom, and you can see the parameters below where it has been added all the parameters for your pseudo atom and zinc as well. Okay, so that particular script will help you to integrate all the parameters of pseudo atom and also the zinc bound into your GPF4 file so that the file can recognize. Okay. So the next command that we are going to do is AutoGrid4. You have to prepare the grid files for the Autodock to run. So the command is AutoGrid4 minus p protein tz dot pdbqt GPF, and then you have to provide minus L protein tz dot glg. So it will create a glg file with all the map files. So whatever you have mentioned on your GPF file, those maps will be created, and you can see that it has been successfully completed. Okay, and all the parameters have been added along with your pseudo atom, along with the zinc, everything, so that Autodock can recognize the parameters while you run the Autodock4. Okay, so now the grid preparation has been completed. Now we move on to the docking parameter file, which is the DPF file, and then you use the prepare DPF 42. That's the file that has been placed in the MGL tools directory. So you can input the ligand name, which is minus L ligand.pdbqt, minus R, which is your protein tz.pdbqt, and then you output it as DPF file, docking parameter file. Okay, so it will prepare the docking parameter file for you, which is ligand protein tz along with the ligands, the small molecule, the protein with 20 amino acids, and tz, which is your pseudo atom, and it will provide a DPF file for you. And then if you open the DPF file, you have all the map files, you have all the parameters like population 150, etc., that you defined by using ADT. So it will automatically prepare it for you, which is the default one. Basically, you can change it later, but this is the parameter file that has been prepared. Now you run the Autodock, which is Autodock4 minus p, your DPF file you have to give, and then it's not minus O because the tutorial is old, so it has to be minus L, and then your ligand protein tz.dlg. And now you can see that your Autodock, the docking has been running, so you can watch it by opening it in a terminal, or you can open the file and you can see that files have been created, and there will be run 1, run 2, run 3. So I think a total of 10 runs. And you can see the binding affinities, which is in kilocalories per mole. Okay. And this is your ligand file, ligand coordinates. So you can also watch it. There's a command called watch minus N2, and then you provide the DLG file. So it will, you can watch it while it was running so that you can track how the files are being created. You have to provide watch minus N2, and then you have to provide a command called tail so that you can see the files have been created or not. So just type in tail. Yeah. And you can see that it's already 9 of 10 poses has already been created, and you can watch it. Basically, watch minus N2 means every 2 seconds you are going to watch how the files are being created. That's the command to track your progress. Okay. It's nothing related to AutoDock4, but it's just a command line argument. Okay. So now everything has been created, and this is your DLG file with all the ligand coordinates, and you can see that it has successfully been completed. Okay. So next we move on to, we open the ADT, which is the MGL tools, and this is your histogram, by the way, where you see all the binding energies and your ranking, etc. The typical histogram. So now we can open the ADT, and you can see the conformation of the ligands bound to the zinc metalloprotein itself. So you open the ADT by using the command called ADT. It will open up the MGL tools, and now if you go to the analyze and then dockings open, then you navigate to that particular directory where your DLG file is, and then you can open it from there. So once you open it, you have to load the macromolecule as well. So now we're going to open the DLG file. Yeah, this is my DLG file, and you can see the initial conformation has been loaded. Now you can load the PDBQT file, which is the protein, TZ, and your ligand coordinates. That's your PDBQT file. And then you can zoom in, and you can see the zinc atoms and even your small molecules. You can navigate to the control panel where you can make it ball and stick model, etc. Based on your visualization perspective, you can make it like that. Okay. It's getting slow because I'm recording, and in the back there has been lot many processes are running right now, so that's why it's being slow. But yeah, so you can open the confirmation and you can see how the ligands have been placed, and you can open this info columns to see the binding energies and all the associated energies linked with this, and you can play the confirmation. And when you go to the protein chain B also, you have the zinc atom right next to your small molecule. That also you can visualize. If you go to the B chain and find in zinc atom, you will find that zinc over there, and then you make it like a spear or something. So it will show up as a spear, and you can also switch off the spear button for the ligand, and you can visualize the zinc atom placed over there. Okay, so it's just you're going to play around with the control panel of the Autodock, and you can visualize the zinc ion also. Okay, so this is how you can prepare the docking parameters for zinc as a pseudo atom, and then by utilizing the zinc metalloproteins, you can dock small molecules into it so that you can see the interactions. Now you can see the zinc atom because I have switched off the spear model for the ligand, and you can see the zinc atom over here. Okay. You can also write the complex. You can see the confirmations like this, and also you can write the complex as complex.pdb file or pdbqt, whatever you need. So once you write the complex file, you can also visualize it by using Chimera also. Right. So there's a button called build current. So you can build the current setup, which is your ligand, which is your zinc and your protein as well. And then there's a button called write complex. So once you build that, you write the complex and save it as a complex.pdb or just complex. You can also give an extension because it doesn't save it as a complex.pdb. But once you save it as a complex, you can also later change it to complex.pdb. Okay. So now you have this complex file. You can just view as a text file, but you can also change the name to complex.pdb, and you can visualize it using Chimera. Okay, now you can open it using Chimera, and you can see that you have the zinc as a blue, color, and your ligand, which is placed right besides the zinc ion, and that's your ligand. You can select it and make it a sphere, and then you select the zinc ion, and I'm going to make red color for this one, so you can visualize, and you can just play around with the parameters in Chimera so you can visualize it better. Okay, that's your zinc ion, which is in red color, and this is your small molecule, which is in sphere. Okay, so yeah, this is how you perform zinc metal proteins or zinc metalloproteins bound to small molecules using Autodock4. I have also the parameters for iron, copper, magnesium, so any number of metal ions that are bound to the zinc proteins. So I will provide all the parameters files, everything except everything once I hit the 4000 watch hours. And you can see that you have the zinc ion over here, which is in red color, and that is your ligand bound to it. Okay, let's say green is the small molecule and the red one is your zinc. You can make it white, and you can play around with the Chimera X. Okay, so yeah, as I said, I have the parameters for all the metal ions. So once I have hit 4000 watch hours, I can provide all the parameters for you, and then it will be easy for you to dock any metalloproteins, not only zinc, not only iron, not only copper, everything you can dock by using those parameter file using Autodock4, and I will provide you that once I hit the mark. Yeah. So let me show you where it is. So I have this folder called test where I have, redefined all the parameters for this. I think in my previous video also I've shown you in the metal docking video, I've shown you where the parameter file is, but this is the file where you can prepare the GPA for any sort of metal ion. And I have this dat file where you have all the parameters, and this is for all the parameters for all the other metal ions that I have. So I can provide you that once I hit the mark, and see you next time. Thank you very much.